Okay, so quickly, who am I? I'm still the same person that has been giving webinars for the past 3 years, except I'm now in a Memfault flannel and I have a little bit longer hair. And so maybe I need to update my profile picture. I was a firmware engineer at Pebble and Fitbit, where I wrote a ton of firmware, but mostly found myself building tools, automations, and helping the, at that time, 100+ firmware engineers at the companies that I was working with, basically do their job better, debug more quickly, and get back to programming, basically. I write a lot of stuff on Interrupt, which is Memfault's blog, where you can find a lot of my content there. And I'm the one who publishes those monthly roundups of interesting things to read about in the firmware world. The things we're going to be talking about today, which is why you all are joining, are metrics. I'm going to cover basically what are metrics in general, why do we use them, what are they, and what is the context of them in relation to firmware and hardware. Then we're going to dive pretty deep into tracking metrics about your battery and battery life and predicting battery life. When you have bad battery life, you want to know what's consuming power. And so we'll talk a little bit about how to figure out what is consuming power within your system, both locally and remotely. Third, another piece that consumes a lot of your power is connectivity. If your device is constantly disconnected, it will try to connect constantly and consume more power. And so we'll basically figure out how to track that. And at the very end, I have answered a few questions that we got in before the webinar and in some best practices section. And I'll go over a few other tips and tricks that I generally abide by as I build out metric systems for firmware devices and what we suggest to do with Memfault. First, I do want to talk a little bit about how Memfault plays a role in metrics, like why is a Memfault presentation talking about metrics? First thing is Memfault is kind of the dashboard where much of your data from your system goes into. And by capturing core dumps and by capturing the current software version that your device is running and the various metrics and reset reasons and battery life information, we can provide kind of a holistic view of what's going on in all of your fleet of devices, whether it's 1 to 10 kind of at your desk or in your office, or 1 million devices out in the field that you really want information on in kind of a holistic view. So this is the dashboard, kind of shows you everything you want to know about your devices at a glance. And then there are 3 pillars of what Memfault provides. We provide the software delivery aspect of things. You need to be able to firmware update your devices first so that you can actually fix issues. And that's when kind of this cycle starts. We have performance monitoring, which is a lot of the metric system, and then device debugging, which is capturing reboot events and core dumps and kind of figuring out exactly what went wrong when your devices experience issues. And so we'll be talking about performance monitoring and then the metric side of device debugging. I have a lot of content here. I may speak a little too quickly at times, but I promise it'll be worth it. And we'll get through it all. So first, what and why of metrics? What are metrics when we use them, and what is the context of them with firmware? A metric is basically a number that you capture when the device is running. And we typically capture, not just one of them and not just a few of them, but generally a lot of them. And we will take all these metrics and generally aggregate them, whether it's on device or in the server. Honestly, in the firmware world, we usually aggregate them on device so that you can send less data to the cloud and that the actual server has to do less work. And what are you going to use metrics for? The goal of metrics is to discover trends. You are trying to discover whether your battery life, increased or decreased from the last software version. You're trying to determine how much time is spent doing a particular operation per hour or per day, or on this software release versus the last one. Some of the things that I generally like to to measure how often a particular task is running. If the idle task is not the task that is primarily running, something in your system is wrong, or your system is maybe using a lot of power. I know Philip from Embedded Artistry loves to track how long a device takes to boot each time. So he will report the duration of boot sequence because he wants that to be as small as possible. You can also count the frequency of errors, how many flash writes and erases you've taken place in case you're trying, worried about the flash chip kind of being too utilized. So all these metrics come into a payload on device, and generally you send them to a server. Memfault likes to call this a metric heartbeat. So a metric heartbeat in our eyes is kind of this holistic payload tagged with the software version, with the timestamp of when it was taking place, how long the actual heartbeat was, and then other various information, what type of hardware, anything else you want to throw at it. And then within that heartbeat are your actual metrics that have been collected from that last hour. And so if you're trying to capture the number of errors that took place, you're going to capture the number of errors that took place in a particular hour, and then send that count in a heartbeat. And then for the next heartbeat, all metrics are reset, and you restart your counters. And with a lot of these heartbeats sent up to a central server from all of your devices in the field, you can actually gather a lot of data about your system and really understand what's going on in all of your devices. So before digging into basically how to the extra data, the secondary level data, let's dig into what the actual metrics of heartbeats are, how you collect them, and what it looks like in firmware. Because for some of these people, for some people, I would assume they've never done this before. And so in the Memfault SDK, it is, you defined your metrics in a header file. And so in this particular case, we're defining the flash bytes written metric, which is an unsigned metric. And we're going to track the battery percentage in an unsigned metric with a range of 0 to 100. Metric IDs are usually 1 to 4 bytes, depending on how you've implemented your library. And then metric values are generally integers or floats. And depending on what kind of compression you're using, Memfault can compress integers depending on the size, but they generally range between 1 and 5 bytes. There are 3 types of metrics I would generally classify them as, and that is going to be a counter, a timer, and a gauge. And so we'll go over each of those, but this is generally the API that you can expect to use, collecting metrics on your own system or collecting metrics through the Memfault library and ultimately service. A metric counter is simply used, you call metric add, you give it a metric ID, which we have a helper, a macro helper for, and then you give it a number that you want to actually increment by. And so if you're counting the number of flash sector erases, every time a flash sector gets erased, you just increment it by 1. And if you're trying to increment it by more than 1, you just pass the actual value. And the beauty of my favorite part about the metrics library in Memfault is by using the Memfault metrics library and this macro that we have. Of course, every library has a bunch of macro magic. Ours is no different. We will take all of the metric names, throw those actually into the symbol file, replace it with an ID that is compact. I think it's usually 1 to 2 bytes. And then by just having 1 or 2 lines of code, we will automatically accept your data, decompress it in the server, and no cloud team involved. It's actually great, but more on that later. So that's a counter. The next thing is timer. It's basically a counter, but we have a helper function that allows you to count time. And generally time on your system is either going to be, milliseconds since epoch or ticks. And so here we're counting the amount of time that the Wi-Fi is connected. It's going to start and then stop both when the Wi-Fi is connected and disconnected. The last type is a gauge. And you can imagine just a gauge kind of like the speedometer. It's not what was the max and mean and average of my speedometer. It's just like, what is the value right now? And so in this particular case, the battery percentage is whatever the battery percent is currently. And you can imagine that as a gauge. So before I go further, and so I can tailor my talk a little bit to the experience level here, I'm curious how many metrics does your team currently collect from production devices? And we can, if it's only local devices, we can assume these are local devices as well. So let me get polls here. I'm going to activate this poll and launch it. I'm hoping to see the 51 plus is my favorite realm of here. All right, I have about half people. I'll wait a few more seconds and then I will hopefully be able to share the results. All right, I'm going to click end. Let's see. So about 25% said none. About half people said 1 to 10. And then 11 to 50 and 51 plus is about a quarter each as well. So yeah, I'm actually quite impressed. So bravo. I'd love to hear, I mean, actually, I'd love to hear more about all the metrics that you guys are collecting, especially the people who are collecting more than 50. That sounds great. Let's move along. And so now what I've been thinking about a lot recently, I've written a doc about it as well, I can share, about battery life. I've talked about it, I've thought about it, and I think we have a pretty good way to capture this in Memfault, and I'd like to talk to you about it today. And so this is how you're capturing battery life from the devices, from whether it's 1 to a million, and then taking that information and being able to project battery life, like how long will this device last given its current behavior and on the current battery and battery life that it currently has. And so a little bit of history, both about what I've done and just batteries in general, is I worked at Pebble. We made smartwatches. The differentiator for our smartwatch was its battery life, whereas the Apple Watch got 1 day of battery life, the Pebble got 7 to 10 days, or in our smallest ittiest bittiest watch, we got 2 days of battery life. And battery life was probably the most important differentiator and feature for people. If a device is out of power, you can't use the product anymore. And so when we had a bug in our watch that would basically cause the battery life to drain in 3 hours, it was a really big deal and we had to fix it. And from customer support cases, it was usually Bluetooth connectivity. That was 1 or 2 on the list of issues that we got from customers. And then it was battery life. And so we spent a lot of time both thinking about battery life, building up infrastructure to measure battery life and monitor it, and then be able for our customer support teams to basically look at it as well. And it's not just measuring the percent. A lot of batteries don't even give you a percent. You need to actually know the millivolts from the battery itself. And you need to come up with a battery curve. Sometimes the battery comes with a curve and sometimes it doesn't. Sometimes you need to build your own. And batteries will also differ between batches. They will lie to you about the temperature. If it's cold, it'll have less charge. And if it's hot, it'll have a different charge amount. One of the issues that we had, which is always fun to hear Chris talk about, was when the vibe motor was active and we took a battery reading at that exact moment in time, it would be as if the battery life had just dropped like by half when the vibe motor was on, or when the LCD was on, or when we were doing a really intensive CPU operation, like calculating, sleep data or step data. All of these operations within the system would cause our percentage reading to fluctuate. And we didn't want that bad data to make its way into the analytic system. And there are many ways to mitigate that. The way that we mitigated it at that point was we wouldn't take a battery life sample during those high-powered CPU events, which you can imagine required its own tracking system. And we would take an average sort of battery life measurement across the hour. And for about a minute or so, we take a bunch of readings and then kind of average that out and then send that up as the battery life at that moment in time. Another thing that I see a lot of people trip up on is just in general trying to track battery life, but tracking the current battery life. And so if a lot of systems are tracking what is the current battery life, is it 50%, is it 30%, and then sending that to a server, it can actually hide a lot of information. And so this is the one that trips people up a lot, is they will send, my battery is at 90%, and then it's at 80%. And they think it's at 70%, but what happened in between these 2 points was the user actually drained the battery very quickly, charged it because it was almost low battery. And then the next time the battery basically reported 70%, and the analytic system is no wiser. It's never going to know that there was a power bug. And the customer support team will just think that this battery, trend was great. And so there are ways to mitigate this. But first I want to talk about generally how you would calculate the average days of battery life that you can expect from a device. And so when customers first come to us at Memfault, they tell us they're capturing battery life in this particular way. They're capturing just the percentage at random intervals and over time. And so these devices, you can actually tell when they were charging, when they were discharging, when were they actually on a charger, pretty much anything at this point. And sometimes they're increasing and sometimes they're decreasing. In this particular case, I would just say it's probably not useful trying to come up with sort of a query to come up with this. We have a couple customers as well who are also struggling to calculate this query with 10,000, 100,000, a million devices, because it's just too difficult and it's not accurate enough either. And so my proposal, and what we used at Pebble to great success, was calculating the percentage drop per hour across all devices. And so within an hour that was our heartbeat interval. We would measure how much percentage drop there was. And so if it went from 80 to 78%, that is totally wrong math, and that's my fault. But 80 to 78% is a 2% drop. 72 to 67 is a 5% drop. What you can do is you can just sum all of these up. You know the time bound window, it's an hour. You know the percentage drop it took place over. And with that, you can actually calculate the projected hours of battery life just by doing a simple sum and average. And the one nuance here is we threw out all readings where the charger kind of got in the way of the reading. And so if a watch was placed onto a charger or was connected over USB or was charging for a brief moment in time or the whole hour, we would just discard that reading, and we assumed we had enough hours to still come up with a very good model. And so you can do this for a single device. You can say, if a single device is dropping 3% per hour, you can assume you can divide it by 100 and get the number of hours it's going to last. But you can also do this for a fleet of devices. And that number is basically unlimited, given that it's a simple sum and division over all devices, and all devices are reporting an accurate sort of percentage drop per hour. It's pretty easy. And the best part, and my favorite part about Memfault, is given that our metrics can be collected in this way and then sort of compared between versions, is we use this to give people a very good insight into whether there was a battery regression or an improvement in before and after software versions. And so in this particular example, you can see that the blue lines represent a 1.0.0 firmware, and the red lines are basically the update, the 1.1.0. The red lines are much larger. And so the numbers are not off, but they're multiplied by 10 here. And so the average percentage drop in the blue firmware was 17%, and the red one was 34%. And so you can see that the battery life drop is almost double per hour in the new firmware. This is a bug. It should be rolled back, and more should be dug into about why. How to actually capture the battery drop per hour? Of course, it's not too difficult, but I just wanted to paint a picture. What you would do in a heartbeat, for the heartbeat system, we call this heartbeat flush and collect data basically every hour. And you would record the percentage at the start of the flush or at the start of the interval, and then at the end of the interval, and subtract the two. And then you would set these two values, both the battery percentage and the battery percentage drop per hour, as gauges, just calling the set function. Of course, there's more logic to be had, whether it's on a charger, whether your vibe motor is also on and going to cause a bad reading. And there's a whole battery doc that I've written on docs.memfault.com about how to capture battery life, which covers most of those scenarios and at least gives you some guidance. And so now we have all this data in Memfault. One of the things we can do, which is also my favorite thing, there are so many favorite things in Memfault of mine, is you can then search for devices that have experienced certain behavior. And so if you actually want to go into Memfault, look at all the devices that have experienced a battery drain of 20% or more in an hour. That is a flag, that is a bad thing that you need to look for, probably some sort of power or driver bug. You can search for these devices. You can click on one. I clicked on one, the first one, and then you can see that there is a very big spike and the drop of the battery in our metrics view. And then since we collect not just battery life, but tons of other metrics, we can see that there's actually other things going on. And so during that battery life drop, the CPU is active and we seem to be writing a lot of flash data. And so if you dug in more, we have people who are collecting tons and tons of different metrics. And so you'd probably see that, oh, maybe the accelerometer is on, or maybe Bluetooth was receiving a lot of traffic during that time. And that's what was causing the CPU to be awake and the flash to be written too often. And so the correlation is the big thing, one of the big powers of metrics, especially when you have a per device view. And so we touched on it here. We wanted to know what was causing bad battery life, but it's consuming power ultimately that is actually what's going on here. And so I want to talk briefly about power consumption metrics and trying to figure out what is consuming power in your system. And so what I hear most often is that this can only be done locally. You generally hook it up to a multimeter, you measure the current out of the device. Of course, it doesn't look like a sealed watch, it looks like a dev board, but you're measuring current this way. And totally, that is a great way. It's almost required at this point. You need to get all of your components, hook them up together, validate that they actually, draw the amount of current that was in the spec sheet, especially both at idle and at different capacities of running. And because a lot of projecting battery life in the early day of a product is basically just math. You need to validate and then do a bunch of math to say, like, we can probably get 5 days or probably get 7 days. We did that a lot at Pebble. So that's one way. Another way to do it locally is what we had at Pebble on the dev board. It's called the Big Board 2. We added a TI chip called the INA 226. Chris can probably talk your ear off about it. Chris, the CTO of Memfault. What we were able to do with this chip is connect a few of our power rails to this particular chip. And then that chip is going to be able to measure the current flowing through those power rails in isolation. And so you could measure how much current the battery chip was using, the accelerometer was using, the gyroscope was using, the compass was using, how much the flash chip was using. All these things had different channels, and it could export them individually on a running system. And so what you can do, and what we had was a couple like scripts that would allow you to plot in matplotlib on Python on your local machine and see that over time on an individual device. And that was really good for just once you knew where to look for an issue, you knew that the accelerometer was maybe drawing too much power or in a particular state drawing too much power, you could then go investigate. But again, this doesn't really solve the problem of how to do this remotely. I gave a talk in our Boston happy hour a couple months ago, and I talked a lot about the battery life and the power consumption. And one of the guys was like, why don't you just use the fuel gauge? And then, so I dug into this a little bit more. We had a fuel gauge as well at Pebble, but we didn't use it. We used it internally, but the problem was it actually consumed too much power when it was on. And so if we have a tiny battery, and one of our watches, we had a 150 milliamp hour battery, turning on the fuel gauge to give a more accurate reading on the percentage and a more accurate, Coulomb counter, actually consumed too much power, brought our battery life down too much. And so we had to disable it. And that seems to be a common trend that we see when we talk to customers. If your device is trying to sip power from a battery, a fuel gauge is not going to work. But for those who don't know, a fuel gauge it's connected between the system and the battery and can kind of count exactly how much current is actually drawn from the battery. And so ideally, you could just do the simple math locally, give an accurate percentage of how much battery life is left. But you can't do that remotely, again, because many people don't use it. So we can collect metrics on the other end, but first we're going to come up with a battery model. And so the way you do that, measure the current with either a multimeter, a fuel gauge, or INA 226. Measure the current of the peripheral when the power is off and the system is running, at a reasonable level. Then exercise the peripheral, whether it's an accelerometer. So turn the accelerometer off, measure the power, turn it on, and have it running at 25 hertz. now measure the power of the whole system. And now you have a pretty accurate picture of how much current that accelerometer takes. And you can do this for sector erases on your flash chip, the Wi-Fi chip, the vibe motor, the LCD backlight. All these sorts of things can be measured in this particular way. And so now, once you have the current usage, maybe it's by second, by minute, or by hour, depending on how long your test was running, or by usage, if it's the number of vibes actually, or the number of mechanical lever presses or something like that. Now you can do this remotely. Ultimately, what we want is a distribution. We want to know, where was our battery life spent? Usually, if you make a mobile device, it's going to be the backlight on the LCD. I guess the fun fact here I learned from one of our Android engineers, that Android actually reports 2 battery lives, or 2 battery sort of projections. They report it when the LCD is on and when it's off, because they're so drastically different. It's almost the primary consumer of battery. Anyways, tangent aside, this is what we want. We want to know where the battery was spent, where the power was actually spent. If you have your rough model on how much current all the pieces that can be power hungry in your system take, and you have the metrics that are counting how long the radio is on, how long the vibe motor is on, how long the LCD is on, you can actually come up with a pretty good estimate about where the power is spent. Of course, it's going to take a decent amount of work and a decent amount of math and a decent amount of upfront cost. But this is how we did it at Pebble, and we used it to great success. And this is how we were able to, during evaluation of all the different components, when we were testing all these different accelerometers and gyroscopes and compasses and different batteries, we were able to pretty accurately say that we will be able to get 5 days, or we will be able to get 7 days of battery life. And so this kind of draws back into, when you have your power model, you can then again kind of assess, if I have a battery drop, I have the CPU is active, that's going to really drain the battery life at this particular rate. And you can come up with answers that way. And so what I alluded to before was spotting regressions in battery life. You can also spot regressions in power consumption. And again, it's not as perfect science as we all want it to be. But if you know on your system that the accelerometer is generally on maybe 5% of the time per hour, and you do a firmware update, and then it jumps to being on for 2 minutes instead of a few seconds here and there, that's a regression. And that's probably a bug in either driver usage, or it's an actual product bug. I remember at Pebble, there was a battery life regression during one particular firmware update to another, and we didn't see it internally at all. We shipped it to production, and then we saw a lot of customers have really bad battery life. We looked into what was actually being consumed mostly, and it was mostly the LCD backlight being on for more time in the new version than the old version. We looked into it more, and we realized there was a very quick change to our settings where the user could change their LCD backlight timeout from 1, 2, 3, or 5 seconds, and we added a 10-second option. And a lot of people had found this 10-second option. And so it was actually a product decision, totally well-intended, that actually led to a battery life regression that made the battery life just unattainable. Our customers actually weren't happy, and so we silently removed that option. But it's similar here. You can measure how often the CPU is asleep per hour, and if that drastically changes between one version to another, it's either an improvement or a regression. I would say that most of our battery life regressions per se, and by regressions, I mean we had 2.0 shipped to customers. It looked great. We got 7 days of battery life, and then we were ready for the next version internally. So we caught a 2.1, and then we ran that internally for 100 employees at Pebble for a day. And a lot of people would complain about battery life. Almost every single battery life issue was around the accelerometer being stuck on the Bluetooth chip not being able to connect successfully, and so it was always scanning, or the CPU had a sleep mode bug. Those three things probably accounted for most of our battery life issues, and we would only see them because we were tracking the metrics on that system. If we didn't have the metrics kind of assessing these systems at all times, we probably would have never found those issues, at least as quickly. We probably would have had to hook it up to an actual multimeter, all the different rails, and then figure it out. But because we had the metrics, we knew, oh, we should be in sleep mode 90% of the time. We were in it 50% of the time. There's a bug, let me go dig in. Okay, that's kind of all I have to say for now about battery life and power. The next thing I wanted to talk about, and I promised, was a little bit about connectivity. And so given that it's so involved in power consumption and battery life, I had to talk about it a little bit. Almost all devices have some form of connectivity nowadays. We realize that devices both need firmware updates, and when we deploy them remotely, we can't keep sending people out to the edges of the world to kind of retrieve the data back from those systems from their internal flash or SD cards. And so almost all systems have some form of connectivity. And we need to monitor that connectivity. We need to monitor how it's behaving, how many bytes are being sent to and from the actual backhaul of the system. A couple of things that we like to measure is the radio channel for Wi-Fi. Did it get stuck on 1, 6, or 11, or did it get stuck on something in the middle that is actually not as ideal? How many failures were there on the actual connectivity chip? If it's constantly failing, there's probably an issue with not even just bad radio or poor signal, but maybe a compatibility issue with an Android phone. Or I say that, it's from my experience. We had a lot of issues at Pebble with various different Android phones from various different countries, running all different versions, all from different vendors. And those are the majority of our Bluetooth bugs that when we saw really high disconnect rates, those were typically the issues. And so on the right, I basically have a how you would count the connections and disconnections of your Wi-Fi chip, for an example. And so some of the more interesting stories we have at Pebble and our time at Fitbit as well is just the random issues that you'd get from customer support requests, but all kind of around Bluetooth. And my favorite one was always the guy who had a Mercedes and was like, my Pebble doesn't work with this. And I kid you not, we would have to go out to his car with a Pebble device, probably with some extra instrumented metrics on it and some extra logging, try to connect to this Mercedes, realize it doesn't really work super well and that it never connected on hands-free, eventually figure out the issues. But that's just one of 1,000 different, matrix sort of events. But what I'm painting here is the complexity is super high. And spotting these regressions is quite difficult. And so one of the recommendations I have for actually spotting power regressions and also connectivity regressions is tracking how much time is spent in each state. And most people can do this using their built-in stack and built in their built-in vendor library. So these are the connectivity states of Bluetooth. You go from scanning through standby and then to initiating or advertising. That is if you're being connected to, or if you're connecting to something else, which is the client, which is the host. And then you can go into a connected state. If you have, and you're tracking metrics for all of these individual states and whether the device is actually off or not, whether the Bluetooth radio is off, you should be able to add up to 100% which states all of these devices were in, which states all these devices were in on any given hour. And similarly, if you track these percentages or counts over milliseconds per hour, you can average these as well. And you can say, of this particular hour, I know that my devices on average spend their time 90% connected. And at Pebble, we had a rough stat. We said, generally, our devices, given the way our customers use our devices, they're 90% connected. If that dropped to 80%, for instance, we knew there was probably a Bluetooth bug. It wasn't that our users just dramatically changed the way they behave overnight. It was a regression. Or if our devices were spending most of their time scanning or it ticked up 5% in scanning time, we knew there was probably an issue in our Bluetooth driver. And so it was a very quick section, but I hope this kind of painted how you would take into account connectivity behavior and painting it to power, since it consumes so much power. And so we'll touch on a lot of this, but I have a best practices section that I want to run through. I realize I have I'm going to probably spend about 5 more minutes on this, and then I will open it up for questions. And so the best practices that I have. Oops, I forgot. Poll first. If you had to choose, which type of issue does your firmware suffer from most? I'm mostly curious about, let me see, poll 2, launch. Mostly curious about this because I can also kind of tie some of the talk in at the very end, and hopefully it spurs your questions a little bit more too. All right, I'll give it another 10 seconds. Wow, very few on performance. However, I would say we get so many questions on performance, and so that's very shocking to me. Okay, I'm going to end poll. The results of this one were connectivity was the most common issue at 40%, and then battery and stability were each 25%. Performance, only 3 people said performance was their top issue. And so that kind of proves my assumption right on a lot of things actually about that. One question we got before this talk that I wanted to address pretty heavily was, does collecting metrics impact battery life? You know, does it negatively impact? It probably doesn't positively impact, but does it negatively impact? My answer is both yes and no, but primarily no. Counting metrics is just incrementing values in RAM. You're probably going to have a couple hundred bytes in RAM. You're going to count some sort of operations every so often. In that RAM buffer, you're going to count, you know, maybe the number of mutex boxes or flash bytes read. And you're operating and manipulating RAM no more often than any of your system, you know, whether that's context switching or RTOS operations. Like, I just don't think it's negligible on performance to both count some and then average a couple values here and there. Some don'ts of collecting battery life, or sorry, metrics, are don't log, you know, kilobytes and kilobytes and megabytes of data. If you do that, you'll have to eventually send that data or compute through it, and then, you know, the CPU will be on more and more, and that will consume battery life. Since we keep suggesting heartbeats to people, persist these heartbeats when you don't have internet connection. And then when you do have an internet connection, or maybe you're connected to the power charger, then go ahead and send the metrics. We have a few customers that spool up their metrics until they're connected to a charger. And then when they have a lot of bandwidth for all those metrics to be sent and maybe connected to Wi-Fi, then they'll send them really quickly. And so what that looks like is we also have a lot of customers that think they want to send a metric every single time they collect a new metric. Maybe they want to sample the battery life every minute, and they'll send that battery life every minute. Maybe they'll send it every hour, or maybe they'll send it every day. I will just say that sending things more often will consume more battery life. And what we suggest to people is send them each hour, or send them each day, or send them when you're connected to a charger. And then your battery life will pretty much not be impacted in any negligible way. But also my main takeaway from using metrics during my time at both Pebble and Fitbit was that our battery life would have suffered for no reason had we not collected the metrics to be able to dig into the battery life to begin with. And so you can either not track how much power is being used or all the subsystems that could impact battery life. And you could say that there's no way we can build a metric system because it would consume more power. But I actually think that is 100% false and the wrong logic to take. By using metrics, you can improve your system, make it more efficient on power, and find the areas in your system in which there is probably a driver bug, or there's too much utilization of flash chip erases, or too much, you know, power consumption in any particular way. And so that's my spiel there. Another best practice, just try to store and send metrics efficiently. I'm going to speed through this. The metrics library for Memfault that we use, from what we found in our investigation, is the most compact way to send data. And so we highly suggest no one use JSON. And then protobuf, cstructs, and the Memfault way to do it is pretty good. They're all pretty compact. But I've never liked the fact that protobuf and a packed cstruct require a sort of schema on the other end. You have to keep track of your protobuf files, or you have to keep track of exactly how your cstruct is encoded. We use CBOR, and we use the symbol files that you give us, or that customers will give us and upload to our service. And we will use that to basically decompact everything or uncompress everything. Less data means less power consumption. And so collect metrics correctly, collect the useful information and store it efficiently. And I don't think it'll impact battery life very often. I alluded to it before, but you can reset the metrics. You should reset the metrics for each heartbeat interval. And the graph here on the right kind of shows what I mean. Over time, a value will just be constantly increasing if this value does not get reset every hour. But the red line is showing showing you the value that is collected over the duration of the hour. And you can more easily spot regressions or increases or decreases. And also it's just easier math. As I showed you before, it's really hard to kind of calculate sporadic numbers, but if you plan ahead and you calculate the drop percentage per hour or the number of flash bytes read per hour, and you reset those values for every single hour, for every hour, the math becomes easier. And you can see and correlate issues between events, and it's really nice. I've alluded to this a bunch, or I've talked about this a bunch. Seeing metrics for a single device is incredibly valuable, and is probably the way we supported our customers at scale at Pebble. We had this sort of per device view, and whenever a customer support ticket was logged or somebody called Pebble, they would bring up this view, see what the customer was complaining about using metrics. If they didn't have the data they needed, they would ask the firmware team to add a couple more metrics. So both customer support and firmware engineers both use this view, and Memfault provides this when they were actually trying to deal with a customer issue. And you can also see, regressions or issues or basically driver bugs really easily. And it's not just only device view. That is super nice. I'll skip this slide. Now you can view issues on a fleet level. And so if you track metrics from one firmware version to another, and you compare them, you can see whether your metrics improved or are actually gone down. And by tracking all these metrics and by making sure you compare them between software versions, I mean, for me, I was able to sleep better at night knowing that firmware version that I'm about to release typically gets better battery life, or typically has a better battery life connectivity rate than the previous one. Whereas if we didn't have these metrics, and sometimes we didn't because we didn't put them in, we got super nervous, and then we had to wait for customers complaining whether their battery life or whether their Bluetooth actually got better or worse. And I think I have one more slide. Yeah, if you don't have an internet connection at that exact moment in time when you're trying to send metrics, persist them, write them to external flash, write them to an SD card. And then when you have internet connection, send them up. And the last one I would say, and what we used to great success, was these metrics don't have to be really well thought out. They have to be deemed useful. You have to make sure that what you're capturing and what you're measuring is ultimately useful and can ultimately kind of drive up and roll up into a KPI. You can't just arbitrarily count the number of button clicks with no actual purpose of it down the road. But if you're calculating or capturing how long the LCD was on, that directly ties into battery life. And they don't need to stay stable between firmware versions. Add a bunch. Since they compress into a few bytes here and there, you can add hundreds of metrics. I know at Pebble, we probably had about 100 to 200 metrics from each device, mostly firmware level diagnostics data, plumbing back to our server, in which we could basically say, this firmware is performing well, or it's not performing well. With Memfault, we make that easy, given that you just give us the symbol file, you write your code, and then we'll show you the data in the backend. There's no kind of cloud team or software engineer or waiting around for a database schema to get deployed. It's all automatic, which is super useful for when you're building nightly builds. Okay, I've talked enough. I'll probably talk more answering questions. I've covered all these things that I wanted to cover: battery life, power consumption, connectivity, all using metrics, and then shared with you some of my best practices tips. Just want to let you know we have a couple more things coming up, or we have at least one thing here. On December 8th, we're going to be talking about how to build out a firmware team with Phil. Oh man, I misspelled his name. Philip Johnston from Embedded Artistry. And I've written what I think is a pretty exhaustive doc on how to track battery life with Memfault. The best practices there. You can find it at this link, but you can also go to docs.memfault.com, find the best practices section, and then look at that battery life doc. It would also be useful if you are not using Memfault. And so thank you. And now on to the Q&A. I believe Colleen and Mariah are going to be helping me with that.
Yeah, we have a few questions from the audience and then a few that people submitted before. A lot related to battery life. So we'll start with one that came in when you were talking about the battery life metrics. It says, what if they charged, but at the end of the hour, the device was still at less charging than the start of the hour?
What we typically did was, if the device ever touched a charger or ever touched, essentially a power cord, we would actually just throw out the data. Because even with a handful of devices, you're going to get enough data to gather information about how long that battery is going to last, from the other 23 hours in which it was not connected to a charger. My quick answer is just throw it out. At Pebble, when we cut a new firmware, we had 20 devices running on it internally. Those 20 devices are capturing 24 heartbeats a day. So now you have, roughly 200 to 300 to 400 hours of data from just 24 hours of running. If you lose a few heartbeats from when it was on the charger, it's fine.
Great, thank you. The next one on battery life says, what would be the best way to figure out what is the discharge curve of our battery if we can't find that kind of data in the battery data sheet?
Cool. Here, oh man, we spent a lot of time on this at Pebble, as you can imagine, because we had to build a battery curve. What we did, we charged the battery to full and then ran a CPU intensive algorithm on it. I think we just found, Stack Overflowed, what is a ridiculously difficult algorithm to compute, and we ran that on the device. And we took a battery millivolt sample every minute, I think. And then obviously that battery and that system would die within the course of maybe 2.5 hours or maybe 4 hours. And then we just took the millivolt readings that we got for that minute, kind of extrapolated it or normalized it over the course of the entire time and said okay, cool, well, 10% in, it dropped by this much millivolts. And then we said that's 90%. Anyways, I think that's what we did. We did this in 3 different ways. We had a high, a medium, and a low drain as well, because batteries have different millivolt readings based upon how much current is being drawn. And so we took those 3 readings from a few different batteries and then came up with a battery curve using that information. I hope that kind of explains what we did. Ultimately, we had an automated system that would do it. It was really cool. But for a bit, it was an intern's job or Chris's job early on.
Thank you. The next one, again, on battery life. So to a few-part question. For devices that are supposed to have long battery life, say 2 years, how do you validate this battery life on the final product? Is it just relying on estimates? Are there any other methods that involve tooling the firmware to drain the battery at an accelerated speed?
Cool. I guess this one kind of touches on the previous one. It's not really. I mean, you can drain the battery quicker, but that doesn't give you insight into how long it's going to last, whether it's going to last 2 years. For this, you have to probably use the local tools and assume that your system is going to run at a stable sort of drain. And then just extrapolate with math. Yes, I will say, and hammer it home, at Fitbit, the way to validate battery life was to wait the full 7 days. And so if our battery was supposed to last 7 days, we actually didn't wait to ship a firmware until all the devices that were running that firmware lasted 7 days. And so we'd actually tell all the firmware people and a bunch of test people, like, charge the device, here's a new firmware, and then report when your device, drains completely, or we'd have that in metrics actually. At Pebble, we took a different approach. We used this drop percentage per hour, and we would validate and ship the firmware within a day of the amount of data. And so we would actually, if the battery looked good, if we were getting a 1% drop per hour, and that extrapolated out, that was more than what we needed, we would say this firmware is going to perform well enough, go ahead and ship it. We didn't have to wait that 7 days. And so in your case, yeah, you can't wait 2 years. You'd probably have to estimate how many coulombs are being drained from this system, and does that work over a two-year life cycle? That's the best way I would say.
Great. On to the next one. So how would you recommend tracking battery life metrics when there are batteries of different ages in the field? For example, the expected battery percentage drop per hour would be different depending on this.
It's a tough one. I truly don't have a great answer. From my experience, these batteries did degrade over time. I think we actually changed our battery curve slightly as our products aged itself. Like when we shipped Gen 1 Pebble, when it was 3 years in, I believe all the watches had been manufactured, all the batteries were generally bad. I think we kind of fudged the numbers down a little bit. What you can do as well is just slowly count the number of cycles the battery has been charged and kind of come up with a model there. I can't say that I have a great answer for this though. If you ever do come up with a good answer, please let me know. I know batteries in larger systems and smart cars, they will have a lot of this logic kind of baked in. They will have a whole integrated circuit or firmware that is tracking how many times this battery has been cycled, what is the battery health, how many batteries are actually bad in the system, and then we'll give you a better accurate reading there. But many of the systems I worked on don't have that knowledge.
Great. Next one, does Memfault support tracking metrics from other non-device sources? For example, a user interface.
Since metrics are just numbers, you can track anything as long as it comes from the system generally. What I'm also interpreting this question to ask is, if I have a hardware device that I'm actually tracking with Memfault, and then some of that data goes through maybe a mobile device and into a website, can I correlate all this information? The answer to that is not quite yet, but we're thinking deeply about it because we want to be able to associate metrics from a device to its gateway, for instance. Like if the gateway is actually an iOS device, we want to know the iOS app version, and we want to know the iOS version itself. But there's nothing pertaining that, like, Memfault isn't going to just be limited to firmware metrics. You can throw whatever metrics you want into our system, generally if it's from the firmware device itself.
Great. Next question says, in which frequency do you suggest to report performance, crash report data?
We typically suggest people do it every hour, 2 hours, or if their battery is very small or their bandwidth is very constrained, then report a heartbeat every day. But I guess it ultimately depends on iteration speed. At Pebble, we moved pretty quickly. We had nightly builds. Most firmware engineers on the team would load that firmware up every single night on their watches that they were wearing. Some wore two Pebbles. And so we needed to collect the data pretty quickly. There was no waiting around for 24 hours to get data. We basically shipped the firmware on people's wrists, and we wanted the data immediately. We also deployed to production, sort of, we had like an every 3 week or every month goal of shipping to production. And so that is going from 0 devices running a firmware to 1 million in an ideal world. If you're a company that these devices last a very long time, they have firmware updates every 6 months, and there's likely no new bugs. You're just trying to assess whether the hardware is healthy, not necessarily this like quickly iterated software is healthy. I would say you can capture things every day and send that up. That's probably the cadence that I would recommend for a non-quickly iterated on hardware product is a day. Otherwise, about an hour. I rambled there. Apologies.
It's great, helpful.
I hope that answers the question, though.
Next question. Are you storing your heartbeat metrics in flash or RAM? If the device goes into deep sleep, then RAM contents are lost, right? If flash, would flash erasing / writing increase the current so that it's not negligible?
Great question. I think I'll try to touch on all of it. The metrics are stored in RAM until the end of the hour or until the end of the heartbeat, basically cycle, I would say. Once the heartbeat is over, then they are generally persisted to external flash. So that in the case of a reboot, we want to basically save as much information as we can in a reboot event. And like you alluded to, if they're in RAM, they'll be lost. We also have customers that either haven't hooked up external flash or it's too difficult. And so they will keep a no init region of RAM in which those can be persisted over reboots. But like you said, if there's a particular deep sleep cycle in which that'll be lost, then it has to be kind of external flash. And is the read and write and erase cycles on external flash kind of going to mess up with, or is it going to draw too much battery? I haven't seen that. I mean, if writing to external flash once an hour consumes too much battery, there's a problem, I would say.
Great. I know we're at the hour, but we have a few more questions. So we'll get through a few more. If that's okay with you, Tyler?
Fine by me.
10 minutes.
I'm having fun.
Right. So if you guys want to stay on, you can and listen to the rest of the questions, or we'll be sending the recording with all of them too after later today. So thank you for joining for anyone that's dropping off now, but we'll continue on. The next question says, what do you capture regarding percentage drop per hour? I mean, if it takes a snapshot of the battery status, how would we know the battery consumption distributions of processes on a device? I'm wrapping my head around, does percentage drop per hour give us sufficient confidence in what's going on a device?
Okay, I'll try to piecemeal this one. Yeah. Every hour or every heartbeat cycle, there's a callback that gets called in your firmware, basically, from at least the Memfault library. At that exact moment, you can query out to the battery or whatever subsystem you have powering you, and you can say, give me the current percentage. Wait a whole hour and say, give me the current percentage again, and you can subtract the two there. And so you're just measuring how much battery has been depleted over this given time. And if it's not an hour and if it's a day, you can measure that over a day. Okay. That's how you would measure the battery percent drop. But now you're trying to figure out what is consuming that power drop. These are entirely different metrics, and they're probably customized to your system, but I can assume that it's probably peripheral usage, peripheral power states, and then tracking how often a task is actually doing work will give you a pretty good insight into what is consuming power. And so at Pebble, we had metrics about whether the Bluetooth chip was on or off, and was it broadcasting, connected, or scanning. Connected was actually using the least amount of power because the interval rates can slow down in the Bluetooth spec. if a device had the accelerometer on for the majority of the hour, we would measure, how often the accelerometer was on, how often it was off, how many samples it was reading. Basically anything that was power hungry, we were measuring in a way that would give us an idea of the usage per hour. We were measuring all of the power hungry subsystems. And it generally gave us a good enough picture. Of course, it's not going to be exact. There's going to be some things that are missing, some peripherals that maybe have negligible power. But as soon as you find something that could paint a better picture of what power was consuming, you should be measuring that as well. I hope I answered that enough. If I didn't, let me know again, or email me at Tyler@Memfault, and I can try to help out.
Great. Another question says, say you collect BLE connectivity data, like percent connected, percent advertising, number of connections, number of disconnections. What are you looking for when you view that together with thousands of devices?
Great, it's a fantastic question. I am generally looking for, I think all of us probably have a golden standard firmware where we were like, this firmware was great. This firmware was too, I remember at Pebble, I believe the 2.4.1 firmware was awesome. It was rock solid in every way. It had the best battery life. We had very little issues with Bluetooth on it, but as soon as we went to 2.5, it was terrible. And so we kind of, when we had this 2.4.1 firmware, we assumed that like, okay, these are the baseline metrics. We've gotten 7 days of battery life, and so we can no longer go behind or below 7 days of battery life. Bluetooth connected percentage, how often it was connected, for our user base was at 90%. We generally have, on average, 3 Bluetooth disconnections per device per hour. And when you plot that across multiple software versions, if you see anything drastically different that deviates from your version or your mental model of a perfect firmware, that's when I would raise an alarm. But yeah, you're right that like, there's no magical number for the number of disconnections, the amount of time connected, how many Bluetooth bytes are actually sent. It's mostly just coming up with a baseline and getting a gut feel. And ultimately, when you start with metrics, it'll be your first slice of data. Your goal should just be to improve each metric as you go, and then see, when it takes too much time to improve a metric, that's probably your baseline at that point. I hope that helps. But yeah, there's no silver bullet there.
Okay, the next one. Is there a good way to tailor the heartbeat frequency depending on use case? Identifying, identifying anomalous behavior on the device and increasing the sampling rate to track. Are there any disadvantages to processing regular data periods on the server?
If this is specifically about Memfault, we should be able to handle those cases. In the heartbeat itself, we also track the duration of the heartbeat. And so we do smart things depending on how long an interval is. And so you can send some heartbeats that are an hour and some heartbeats that are 24 hours, and we can give you information, based upon that. And there's nothing preventing that from changing. Is there? I want to say that is hard coded in a macro in our library, but there'd be nothing preventing us from basically, changing that in the future. There's nothing kind of forcing that. We do recommend people just keep the same heartbeat interval, because ultimately, like, I don't actually think capturing metrics and heartbeat metrics more frequently does much. You can maybe turn on different metrics and different verbosities of certain metrics, like, oh, you only want to get into measuring the actual Wi-Fi status code responses if you're actually experiencing a Wi-Fi bug on this particular firmware. But ultimately, you're just trying to count the number of things that are happening and whether you send that data every minute or every hour, it's kind of all the same. It should roll up to the same amount of time period or same amount of data. Yeah, I don't think I have anything else to say there. Good question though.
Great. Just a few more.
Okay.
Why do you not use battery backed up NVRAM instead of flash?
I think it's all dependent on hardware. I'm mostly speaking to my experience and to what many of our customers use. But if you have places where you can put metrics that will survive reboots, then go for it for sure. All depends on like how much space is on that as well. I've seen some systems have very small amounts of RAM, and some have plenty.
Great. The next question says, is it possible also to monitor the lifetime of batteries used in PV systems using the tools developed by Memfault?
Nothing is stopping you, but nothing is built out, I would say. Yeah, Memfault is going to be a system in which you can send firmware metrics, firmware crashes, firmware reboots into, and kind of whatever you want to discover from that information, you probably can. Come chat with us. I'd be curious more about this use case.
Great. I think we had, sorry, lost the Q&A window. A few more that were submitted previously. Sorry, lost the window. Okay, here we go. We have a scenario, this was one submitted, in which our product is being installed in the customer system in different zones around the world in large numbers. We want to know how to manage the field failures and give resolutions smartly with minimum support engineers available. How would you go about doing this?
This one I would truly say just message us at Memfault. This question it's kind of touching on the holistic monitoring of devices. It's not just metrics. And so we haven't seen many other systems, and we like ours a lot actually at Memfault. Instrument the firmware, capture the crashes that are actually taking place on your firmware, kind of wherever it is, and then monitor with metrics what's actually going on in the system and at runtime. And using the way that we've kind of orchestrated this, the data pipeline and how data gets collected from this SDK and our library that you integrate into your firmware, just make sure that data eventually gets back to our system, whether that is through an SD card or through LoRa or through BLE or Wi-Fi or Zigbee or whatever gateway system you have. As long as the data makes it back to us, we will be able to process it. And we've had great success to that. Like Pebble devices were deployed all over the world. We didn't have technicians. These devices were sometimes offline for weeks or months on end, and they would upload their analytics at a later date, and everything seemed to work fine. But again, message us. That sounds like a very interesting use case.
Great. Just two more questions. The next one is, for cellular-based IoT devices monitoring assets, how important is it to monitor device signal strength, as these don't tend to change much for stationary assets?
For stationary assets, true. For non-stationary assets, that's the opposite of true, I would say. For stationary ones, it's probably still good to monitor signal strength because you're probably trying to compare device A to B, which are deployed in two different regions. But yes, if you're trying to compare the metrics of device A to device A, over the course of time, it's probably not going to change. But you're probably going to want to figure out whether signal strength for device A through B or device A across the entire fleet changes or affects other parts of your system based on that signal strength. I would still measure it. I wouldn't devote a ton of metrics to it or measure it in a bunch of different ways, but get an overview of it. For moving devices, the signal strength and LTE parameters are one of the most important things to capture. LTE is widely deployed, but very different everywhere you go.
Great. And the last question says, what kind of interface do we need on our IoT devices to interface with your platform, with Memfault?
You just need, well, our firmware SDK is a C library. And so we've embedded that into anything from bare metal to embedded Linux. We have an Android platform or Android SDK as well. Integrate one of those two. We also have an embedded Linux product as well. It's slowly being rolled out. Integrate that. These libraries and SDKs will generate data that eventually needs to make it back to the Memfault service through an HTTP endpoint. And so I guess the required interface is include the library and then get the data back to us. It doesn't need HTTP. It doesn't need a certain software stack. We'll integrate with almost any software stack running as long as it's on supported hardware, because we mainly integrate with the hardware and the chip level sort of integrations like Cortex-M or ESP32 or RMA7, that sort of stuff. So let us know, contact us.
Great. That's all of the questions that we had. Most of the other ones that were submitted beforehand were answered by you earlier, Tyler. So if anyone has any other questions that were not answered that you think of after, you can contact Tyler or the other Memfault engineers in the Interrupt Slack group. We'll share that link in the email after, along with the recording link, the slide deck, and the other resources that Tyler mentioned in this talk. Thank you all for joining. Do you have anything else, Tyler?
No, not really. Thank you all.